Okay, hello everybody. This is trigonometry. I'm Mr. Stroop, and we'll begin with angles and radian measure. So what is an angle? Well, I suspect you've seen them before in triangles, right? So there's that word angle in the word triangle, and tri means three, so it's an object with three angles, right? So there's one angle, here's a second angle, and here's a third angle. And in the beginning, we want to assign some sort of measurement to these angles. So there's different types of angles, different size angles, and the angle size doesn't have anything to do with the length of the actual sides here. So the angle we worry about is right here, and that angle is no different than this same angle, but with longer sides, right? So it doesn't change just because the sides become longer. So this angle here and this angle here are the same. Okay, so we want to develop some sort of way to measure that, and we'll have degrees and then radians later on. Okay, so let's be a little more specific about angles in general. Okay, so here we go, angles. There are two sides to the angle. There's the initial side and the terminal side. So just some general facts here. We can take any piece of paper and draw two lines connected at one point. This point here we'll call the vertex. And there's two sides here. Each one of these line segments represents a side. So this side here we'll call the initial side. And this side here we'll call the terminal side. And here in the middle will be the angle. And I think in terms of compasses, when I was younger in our classes, we would have to use compasses and protractors, and it was a lot more hands-on back then. If you go into engineering, you'll probably have to buy some sort of engineer's kit where they'll have all kinds of tools like you're seeing on the screen right now. And, you know, when you open up a compass, it makes an angle. And you could actually draw that angle down onto a piece of paper. So if you're in the drawing and that sort of thing, architecture or whatever, eventually you'll have to deal with these things, the compass. Okay, so that's what I think of when I look at these angles. I think of a compass opening up a certain angle. And this symbol here that I put is called a theta. So this thing is a Greek letter, capital theta. Okay, great. We're going to want to standardize the angle. We don't want it just floating around in the plane. We're going to put it in the XY plane in particular. Okay, so we'll have kind of a standardization, called a standard position. And we're going to put the initial side on the positive x-axis. Okay, so here is our XY plane drawn out. That's the x-axis, y-axis. So here's the x-axis. Here's the y-axis. We're always going to put the initial side on the x-axis. Okay, and then thinking like a compass, you open it up and to whatever degree you want. So I'll open it like this, and we have this angle theta. Okay, if you open it up in this direction, it's a positive angle, and if you go in the other direction, it'll be a negative angle. So if you go like this in this direction, your angle will be negative. So for instance, if I went like down here or something like that, so some other theta here, that would be a negative value. So positive opening, I guess, in the counterclockwise direction, negative going in the clockwise direction. Okay. Let's talk now about measuring angles, and we're going to first introduce degree measurement. Okay. So section 2, measurement of angles. And we begin part A with degrees. Okay, so what we're going to do is basically take a circle and cut it up into 360 parts. Okay, so 0, and then maybe 1 is right here. There would be 90 degrees right here. 180 is right here. This would be 270, and then if you go full circle, it's 360 degrees. If you have some crazy relatives who love cars, you may have heard them say, well, I just did a 360, or maybe even skateboarding, right? I think a long time ago when I was a kid, I did a 180, on my skateboard. Those things, those are degrees, okay? So let's be a little bit more careful and define them in terms of initial and terminal sides. So this angle right here would be a 90-degree angle, and we usually notate it with a little box in between the initial side and the terminal side. Okay, so this is 90 degrees, and it's also called a right angle. Okay, 180 degrees would be if I opened up sort of the quote-unquote compass all the way to the other side here. This angle then, opening in that direction, the angle theta would be 180 degrees. You don't have a special name for that. There are obtuse angles and acute angles. So an angle that's in between 90 and 180 degrees, in between these two angles that I've just drawn, is called obtuse. So I could just give you an example of an obtuse angle. So it's bigger than 90, but less than 180. Okay? So this guy, theta, is bigger than 90 degrees, but less than 180 degrees, and it's called obtuse. You may have seen, what is that, The Family Guy, and then they're making fun of this scene from Shawshank Redemption where the guy says, "You shouldn't be so obtuse," and they show the guy making this with his body. He makes an obtuse angle. You have to watch. I don't suggest watching that show. It's kind of crude, but anyways, if you have seen it, you know what I'm talking about. The acute angle looks like this. So here, this would be an angle that is in between 0 and 90 degrees. And it's called acute. Okay. So that's degree measurement. That gives you a pretty good idea how that works. So the other kind of measurement is called radian measurement. And it's a ratio between the arc length and the radius of the circle. So if let's put a circle here in the XY plane. Okay. And circles have a radius. The radius is the distance from the center of the circle to the outside of the circle. So maybe this distance right here would be the radius. Okay. And then the arc length is sort of associated with circumference, right? It's a distance around, walking distance around the circle, except arc length is kind of just maybe not all the way around. So this segment that I'm doing in red, the distance of that would be called arc length, and we usually give that the letter S. Okay, that's my cursive S, which I just butchered. Let me try to draw it again. So cursive S for arc length. Okay. Then if you want to, you can talk about angles with regards to those two variables. Okay, so let's make an angle going from the positive x-axis, the initial side, to the terminal side. I'll put here where I drew the radius. Let's call this whole thing theta. There's a relationship between these variables that maybe you remember from geometry. It's the standing room only equation. Okay, so standing room only. And you can see arc length S, R radius, theta is the angle. From here, we can get an expression for theta by dividing both sides by R, right? So if you have S equals R theta, you can divide both sides by R. And flip-flopping the sides, you end up with theta equaling S over R. Okay, and that's the units of that thing are radians. Okay, so It's a ratio of arc length to the radius of the circle. Okay. Okay, we want to go in between radians and degrees. So degrees are, in my work, have usually been used, and my job as a teacher here has usually been used for applications. And then radians is more like math without applications, like pure math, they'll call it. Okay, so we want to build a relationship between these two so you can go from one to the other. Your calculator has a little button to go from one to the other. Make sure you're in the right mode. That will be an issue later on. But let's talk about the relationship, right? We want to be able to go from one to the other, and we want to be able to do, in other words, conversions. Okay. Okay. So first off, what is one complete kind of rotation in terms of radians? Well, if you think about the circle, and I want to go all the way around with degrees, that's going to be 360 degrees. Okay, that angle going all the way around, theta is 360 degrees. I want to get the same measurement but in radians. Okay, so from above, theta is equal to S over R. And in this case, we want to go all the way around the circle. So if we travel the full circle, the arc length, S, the walking distance around the circle, is just going to be the circumference. And you may remember the circumference formula from geometry is 2 times pi times r. Okay? So in this case, for one full rotation, theta will equal S over R, in other words, 2 pi r over r. And then we allow the r's to cancel, and we have our measurement in radians. Okay, so one full rotation around the circle is 2 pi radians. And from there, we can make a relationship between degrees and radians, right? So we could say 360 degrees equals 2 pi radians. And also note that if you divide both sides by 2, 180 degrees equals pi radians. Even further, you can even say like 90 degrees is pi over 2 radians. Okay. The second relationship is what we're going to be using as our conversion factor. So if you've done a lot of conversions, maybe like kilograms to grams and stuff like that, you probably dealt with these types of factors before. So we'll have two conversion factors. The first we use in going from degrees to radians. So you're going to have some angle in degrees. And to get it out of degrees in the radians, you're going to multiply by pi over 180. So pi radians over 180 degrees. Okay, so that's the first one. The second one is going from radians to degrees. And I'm going to show you some examples here in a sec, if you're kind of not following my notation or whatever. Degrees. But the important part is this part right here. So if you're going from degrees to radians, you want that. If you're going then from radians to degrees, you'll begin with some angle in terms of radians. And then you're going to multiply so the radians kind of cancel out. So this time you need 180 in the numerator and the pi in the denominator. But the conversion factor, again, the main part that we need is this part here. Okay, so let's do some examples here. I just take these from the book. So first let's try converting from degrees to radians. And they're going to give us 60 degrees for our first problem. Okay. So, you know, I think I need the degrees to cancel out. So if I multiply by a factor, I want the degrees in the denominator. I want to put 180 degrees in the denominator and then pi up top, pi radians. So the degrees will kind of cancel out and you're left with radians, right? So these degrees cancel out and, you know, pi is in terms of radians. And we end up with 60 pi all over 180. And of course you want to simplify that into pi over 3. Okay. Let's look at another one. So get some negative angles here, negative 300 degrees. And we also want to start thinking about, you know, what does that 60 degrees look like? What quadrant is that in? Well, it's going to be about right here, right? Because if you go all the way to the y-axis, it's 90 degrees, but this would be about 60 degrees, which is also pi over 3 radians. Okay. Negative 300 degrees, to get there, so I kind of remind myself, from here to here is 90, from here to here is 180, from here to here is 270, and then I'll have to go a little bit more, right? 360 degrees would be all the way around. I'm just going to go to 300 degrees, so it's somewhere in there. I'm not exactly sure, but that would be negative 300 degrees. Okay. Right, so let's go ahead and convert it then. So, you know, 300 degrees, I want the degrees in the denominator of my factor. Put the radians up top. And then we'll have negative 300 over 180, and I went ahead and reduced that. It's 5 over 3, and don't forget your pi, 5 pi over 3 radians. Okay. Let's do another example, and this time we'll use the other conversion, right? So we want to convert this time from radians into degrees. Let me make sure I'm actually recording. That's always a bummer when you figure out you're not recording. Okay, we're good. So this time they're going to give us some radians, something in radians, so pi over 4 radians. And I want to convert. Okay, so pi over 4 radians. The conversion factor, I want the denominator, the bottom of the fraction, to be the radian part this time. So the radians cancel out. And then in the top, I'll put the degrees, 180 degrees. Sorry for my writing. Then the radians cancel out, and you're left with something in degrees. The pi's will cancel out. Okay, so the pi cancels with this pi. And you end up with 180 over 4 degrees. And if you put that into your calculator, over 4 degrees, that'll be, I believe that's 45 degrees. Okay, so where is that? That perfectly cuts the second quadrant in half right here. Okay, so 90 degrees would be a right angle. Half of 90 degrees is 45 degrees, which is also pi over 4. Okay. Okay. You could have something like 6 radians. So it's not always going to be in terms of pi, but if you think about it, what is pi? Pi is like 3.14159, something like that, right? So you can always think pi is about 3.14 radians, which is going to be approximately 180 degrees. Okay. So in this case, 6 radians is way around, right? It's almost 360 degrees, because if 1 pi is 3.14, 2 pi is probably going to be about 6.18, right? So you just multiply the radians by 6.1, and that should be approximately 360 degrees. Okay, well, 2 pi is 360 degrees, but 6.18 radians will be approximately 360 degrees. Okay, so 6 radians should be about 360 degrees. So let's see. So we start with 6 radians. I need to multiply by something. The denominator needs to be the radian part to make the cancellation to get your appropriate units. And the top, I'm putting 180 degrees. Okay. And so I'll end up with 6 times 180 is 1080. and then downstairs we have pi, and the new units are degrees. If you put that in your calculator, you'll get approximately 343.8 degrees. So yeah, it's pretty close to what I was thinking, 360 degrees. It's almost full circle. 6 radians, almost full circle. Okay, so what I've been doing kind of to the side here is trying to connect all of these degree measurements to and the radian measurements to the XY plane. And ultimately, hopefully, you'll be able to kind of move around the XY plane by these angles, okay, and with regards to the standard position. And that's kind of what we want to investigate next, angles and standard position. Okay, so just moving around the XY plane by certain number of angles. And if you go in this, again, if you go in this direction, you're going positive. If you go in this direction, you're going negative. Okay, so first I'll just move around by 90 degrees. Okay, so the first angle from here to here, 90 degrees, that will be right here. So I can label that 90 degrees. But you could also think of it as pi over 2, if you look above pi over 2. Okay? And then if I move another 90 degrees, where do I end up? Right here. That'll be 180 degrees, which is just pi, right? And if you think about it, pi over 2 plus pi over 2, well, that is pi. Right? And then if you go another pi over 2, or 90 degree angle, you'll get 3 pi over 2, right? So this next angle right here would be 3 pi over 2. And then if you go another 90 degrees, and assuming we started at 0 degrees, if you go another 90 degrees from 3 pi over 4, you'll get 4 pi over, you'll get, that should be 3 pi over 2, I'm sorry. Yeah, so this guy down here is 3 pi over 2. If you go by another pi over 2, you should get 4 pi over 2, which is the same as 2 pi. Okay, so that's the first, kind of way to travel around the unit circle. You can also travel by pi's, right? So you could go 1 pi all the way over to here, and then 2 pi will bring you back to where you started. Okay, and so there's a lot of angles that are kind of the same. They call them coterminal angles, and we'll be worrying about those here in a little bit. Okay, let's move around the unit circle going by 45 degrees, or pi over 4s. Okay, so here's 1 pi over 4, or 45 degrees if you want. I'm gonna go by radians. Okay, and then 2 pi over 4 is at pi over 2. Right, so this is also 2 pi over 4. Then 3 pi over 4. And then 4 pi over 4. So 4 pi over 4 is also pi, the same numbers. 5 pi over 4 is in the third quadrant. 6 pi over 4 is the same as 3 pi over 2. Um, 7 pi over 4. And then 8 pi over 4 will bring you back to 2 pi. 2 pi is the same as 8 pi over 4. Okay. And you could also think of pi over 4 as 1/4 revolution of the circle. So you're thinking basically what times 2 pi is equal to pi over 4, and that tells you how many times you've kind of gone around the circle. So if you divide both sides by 2 pi, the angle x, I'm calling it, you'll have pi over 4 times 1 over 2 pi. So that would be 1/8 basically of the circle, or 1/8 revolution. Okay, so you could always play that game to figure out how much of a revolution you've moved around the circle. So for instance, pi over 6, if you're trying to figure out where the heck that is, how much of the circle is pi over 6, you could divide both sides by 2 pi, or in other words, multiply both sides by 1 over 2 pi. The pi's cancel, and it's 1/12 of a circle. Okay, so 1 1, 2, 3 would put you at pi over 2. So let's do the pi over 6's. Let's count those out. Let's put those in yellow, I guess. Okay, so here is 1 pi over 6. Here is 2 pi over 6, which is also, guess what? Pi over 3. Okay. If you're more of a degrees person, I'm hoping to push you more towards radians, but if you are kind of stuck in degree mode, pi over 3 in degrees will be, pi over 3 radians will be 60 degrees, and pi over 6 radians will be 30 degrees. Okay, just in case you're worried about that. Okay, so pi over 6, this would be 2 pi over, 2 pi over 6 is pi over 3. And then we have 3 pi over 6, of course, then is also pi over 2. And then 4 pi over 6, which is also 2 pi over 3. And then 5 pi over 6. And then 6 pi over 6, of course, it's just pi. And then 7 pi over 6. And then, of course, 8 pi over 6, which is also 4 pi over 3. 9 pi over 6 is the same as 6 pi over 4, which is the same as 3 pi over 2. 10 pi over 6. And I don't expect you to memorize this thing. I just expect you to be able to move around the circle using these elements, these units. So going by pi over 3s, 1, 2, 3 pi over 3, 4 pi over 3 is right here. Anyways, this will be 11 pi over 6, and then of course 12 pi over 6 is just 2 pi. 10 pi over 6 is also 5 pi over 3. Okay. So you can also move around the unit circle going by pi over 3s. Let me put those in green. So here's 1 pi over 3. Hopefully you can see that. Here's 2 pi over 3. 3 pi over 3, then is just pi. 4 pi over 3. 5 pi over 3. And finally 6 pi over 3 takes you back home. What else? So going in the other direction, you're just moving negative. So if you wish, maybe I can scroll down and get this. That picture's getting a little overwhelming there. If you want to go in the other direction, so this would be negative pi over 4. This angle right here, and then negative 2 pi over 4 would be right here, negative 2 pi over 4, which is also negative pi over 2, of course. Okay, and then here's negative 3 pi over 4. Hopefully that's kind of self-explanatory. So negative pi over 4 is coterminal with 7 pi over 4. Okay, so those are kind of ending at the same place in the xy plane. Okay, let's look at some examples from the book where they ask you to plot some of these angles. So part A, plot theta is negative pi over 4. Okay. Again, you can think in terms of revolutions if you wish. You could think of, okay, what times 2 pi ends up giving you negative pi over 4. Okay, and you just solve for x. So multiply both sides by 1 over 2 pi. The pi's cancel. Negative 1/8 of the circle. Okay. So thinking in terms of 8s, 1, 2, 3, 4, 5, 6, 7, 8, it'll be right here is negative pi over 4. I think I just did that above anyways. Okay, so this angle theta here is the negative pi over 4. Let's try another one. This is part D. I think this is checkpoint 4 in the book. Let's call it check 4. This is the Greek letter gamma, and they want you to plot 13 pi over 4 this time. And again, if you want to, you can convert it to revolutions of a circle like I did before. Okay, so I'm going to count around. There's other little clever tricks you can do, like you can keep reducing it by 2 pi, so 13 pi over 4. If you subtract away 2 pi, and then you got a common denominator here. What is 2 pi? That'll be 8 pi over 4. 8, that's 5 pi over 4. It makes it a little easier to figure out where it is. So here's 1 pi over 4. Let me do this in blue, I guess. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. Okay, is this angle. But that's coterminal with 13 pi over 4. So let's find 13 pi over 4, and I'll do that in red so you can see how this coterminal issue works. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm redrawing 10, 11, 12, 13. Yeah, so I ended up back where I wanted to. So if you kind of we're watching what I traced out. I'm going all the way around, and then I came back around to right here. And that gives me the angle 13 pi over 4, which was coterminal with 5 pi over 4. Okay, so coterminal, what does that mean? It basically means if you just add or subtract 2 pi to the original angle, you'll kind of end up exactly where you started, because what 2 pi is 360 degrees. It's just one full circle. Okay, so if you ended here and you did, right here, I'm drawing again in red, or maybe let's put it in some other color, like yellow. If you end here and you add another 2 pi to it, what happens? Well, you go right around the circle and you end up right back where you started. If you subtract 2 pi from it, it's just going to go in the other direction, right? So it'll go in this direction and come back where you started. And you could continue to do that over and over and over, and you'll still be coterminal. Okay, so let's make that official and talk about coterminal angles. Okay. And so if you have an angle theta, to find a coterminal angle, you can always add in, so plus, or you can subtract away, minus, multiples of 2 pi. So the way to say multiples of 2 pi is just to put this extra constant in here, this k. And we assume that k is a counting number or a negative counting number, what they call integers. Okay, so k is in the set of integers, which is, dot, 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 comma, -2, -1, 0, 1, 2, 3, dot, dot, dot. And of course, if you did a little bit of set notation, you may have seen this symbol for integers, which is kind of like a capital Z, bold Z, but in handwriting. Okay, so that might be weird. Just disregard it if it's weird. The angle with respect to degrees, then what you do is you take your starting angle and then you subtract in multiples of 360 degrees. Okay, with this k value, that could be 1, 2, 3, 4, whatever. Okay. Okay, so let's look at some of those problems, and we'll look at, I think this is number 59 from the book. They want you to find coterminal positive angle. Find an angle that is in between 0 and 360. So theta is greater than 0 but less than 360. They say positive angle. Or if they're talking about radians, they want the angle in between 0 and 2 pi. And usually if it's in radians, you don't write the units, okay? It's only when you're dealing with degrees that you'll put the little degree symbol. Okay, so number 59, negative 150 degrees. And so to get into the range here, we need to increase it. So we'll just keep on adding 360 until we get something in between 0 and 360. Okay, so we start with negative 150 degrees and add in 360. And we end up with 210 degrees. okay, which is definitely in our interval. So that would be our answer. Okay. The video quiz, so you have a little quiz in every video that you have to write on a piece of paper, and then you'll turn in the quiz from the video quiz from 4.1, 4.2, 4.3, 4.4 all on one piece of paper. And there's a little button in Blackboard for your submission, and each quiz is worth then 4 points, 1 point for each video lecture. There's 1 question in each video, and you'll turn it in 4 at a time, right? So you put all 4 on one piece of paper, take pictures, upload it, convert to PDF, and submit it to me through Blackboard. Okay, so the first quiz is do this kind of problem. Find a coterminal angle. In between 0 and 360, where our angle is 580 degrees. Okay, so find a coterminal angle in there. I just need to write this down for myself so I know. Okay. Let's look at number 62 from the book. And this time I'm given negative 760. So again, you just keep on, for the quiz, you have to subtract 360, right, to get it in between 0 and 360. For this, you're adding. So I'll go negative 760 plus 360. That'll give me negative 400. That's still not in that range, so I add another 360, and that'll give me negative 40. Still not in the range, so you add another 360, and you get 320, and that will be the answer there. Okay, so in between 0 and 360. Let's try a radian version. So this time we need it in between 0 and 2 pi. We're given 23 pi over 5, and we're subtracting away multiples of 2 pi, if you wish. So minus 2 pi. Okay. I need a common denominator with 23 pi over 5 minus 10 pi over 5. That gives me 13 pi over 5. 13 pi over 5 is still greater than 2 pi, right? 10 pi over 5 is equal to 2 pi. This is more than that. So I have to do it again. And I'll just go ahead and the common denominator of 5. So I end up with 3 pi over 5, and that'll be my coterminal angle. Okay. Finally, then, we're kind of back to this mysterious formula that I use to introduce the radian measurement. Okay, so it's the length of a circular arc. And here's our picture. It's a standing room only formula. Okay. So I have some sort of circle and some angle here in the circle, and I want to know the distance, basically the walking distance from here to here in yellow. Okay, and that walking distance is S. And then this circle will have some radius r. In order to figure out S, you have to multiply r times theta. And one particular sort of peculiarity of this is that theta needs to be in radians. Okay, so theta must be in radians. Okay. So let's look at one of these. This is checkpoint 8 in the book. And they're trying to get us to figure out the arc length, given that the radius of the circle is 6, and we're looking at 45 degrees as our angle. Okay. So if you want a picture, that's fine. You can draw a picture. There's radius 6, 1, 2, 3, 4, 5, 6, and the angle 45 degrees. So I'm basically looking for this distance right here, from the x-axis to this angle the terminal side of 45 degrees. Okay, so the arc length S is 6 times 40, well, you have to be careful, right? You have to convert 45 degrees into radians. So 45 degrees times pi over 180 is going to be pi over 4 when all is said and done. So I'll go ahead and multiply 6 by pi over 4. And we end up with 3 pi over 2. And because the radius was given in inches, which I didn't note that, I should have, I apologize, the arc length is also going to be a distance in inches. Okay. Okay, so you can kind of think of the radians as kind of unitless, and the 6 is in inches. So, okay. One application you'll see in physics is working with linear and angular speed. Okay, so linear versus angular speed. And the best way I can think of explaining this is using kind of a rolling circle. Okay, so you have a circle kind of like starting here, and then it's rolling down the x-axis. Okay, the speed of that going from position 1 to position 2 with respect to some time is the linear speed. Okay, the angular speed is kind of the rate at which the kind of angle opens up. So you imagine there's kind of like a closed compass sitting right here, and then as it rolls, there's kind of an angle that opens up. So originally it was like that, but as it rolls, I'm trying to figure out how it's going to roll. This part kind of angles up. You'll have this theta angle here opening. So as it rolls even more, it'll open even more. Okay, and the speed at which that angle opens is what I would call the angular speed. Okay, so maybe as it goes right here, it opens a little bit more to right there. So you see it gets a little bit bigger as it rolls down. Okay, we can then define the angular and the linear speed. So linear speed first is defined as v equals, so that's my cursive v, arc length over time. Okay. And then the angular speed is going to be the angle over time. So we'll call angular speed, and I misspelled angular. We'll give the Greek letter omega, which looks like that. Looks like a W. That's just the angle over time. Okay. Okay. You could connect these two things together by doing a substitution with our standing room only formula. So note the standing room only formula, S equals R theta. We can take the linear equation, V equals S over T, and replace the S with the R theta. Okay? So you'll end up with R theta over T, which you can rewrite as R times theta over T, which then we could rewrite with angular speed, R times omega. Okay. So we have this other formula for free where we connect the linear and the angular speeds. Okay, let's look at an example with a windmill. So you see windmills now a lot more than you used to, giving us wind power. So we have this sort of windmill type thing that we see sometimes, like on 480, way out there, there's one. The length of the propellers is 10 feet. Okay, so I put this length here is 10 feet. And we're told this propeller zips around at 4 revolutions per second. And we want to find the linear speed in feet per second. Okay, so first thing we note is that one full revolution is equal to 2 pi radians. Okay, so we can convert this 4 revolutions into radians, right? So if we have 4 revolutions per 1 second, we can make a conversion factor where we cancel out the revolutions part and leave it in radians per second. Okay, revolutions. There's 1 revolution and 2 pi radians. Okay, so the revolutions kind of cancel out, and so the windmill is going 8 pi radians per second. Okay, to get then the linear speed, we can use this formula here. Okay? We just multiply, because what we have there is the omega, the theta over time. The angle is theta over time. Here is in seconds. The theta is in radians. So to get the linear speed then, v, all I have to do is multiply r times this thing, which is actually omega. Okay, so r is 10 feet times the 8 pi radians per second, and we end up with 80 pi feet per second. Okay. Okay. Let's look at maybe 1 or 2, what you're in for on my math lab, of course. Looks like there's a lot of questions, but I deleted a lot of them. So there's probably only like 20 or 30 in there. For instance, if you click on number 40, yeah, oh geez, it wants me to re-log in. So, high security levels here. Okay, I just logged in. Why are you doing this to me? Okay, so let's try this again. Okay. So say the question has been removed, but you get full credit for it. So it's not in there, so don't worry. You see all these questions, you're like, oh no, I'm going to go insane doing homework. No, I removed a lot of them. Okay, let's try this guy. So I always kind of try to throw in some applications for you in my math lab. Let's see what they got for us. Okay, let me move this around. Hopefully I can see where the heck the homework is. The minute hand of a clock moves from 12 to 4 o'clock, or 1/3 complete revolution. So here's 12, 1, 2, 3. It's kind of at 45 degrees, but we're moving a little farther to 4. So it's down here somewhere. That's 1/3 of a complete revolution. How many degrees does it move, and how many radians? So for degrees, it's just 1/3 of a full circle, so of 360 degrees. So that looks like 120 degrees. So we just come over here and type that in. Looks like they put the degrees in there for you. And then what else? Radians. So 1/3, so a complete circle would be 2 pi. So you want to go 1/3 times 2 pi. And that'll be 2 pi over 3, of course. We needed a fraction in there, and then we need 2. Whoops, it gives us that. There it is, 2 pi over 3. Check the answer. Yay. Okay, and then we did this one. Let's see if there's anything else. Oh, this one. 2 cities on planet Earth, A and B, are 8,500 miles apart. So if we cut the Earth in half and kind of laid it flat, what we're after, or what we're looking at, is kind of a part of a circle here, where this is A, this is the surface of the Earth, and then here's B, and then C is at the center of the Earth, and then there's some angle theta. A and B are 8,500 miles apart. Okay, so this is 8,500 miles. And the radius of the Earth is apparently 4,000 miles. Okay, so this is 4,000. And you know, it's just a part of the full picture. Here's the cross section of the planet Earth. Okay. And what are they asking for? They want to know the angle. So the standing room only formula, I believe, is what we want to go after, what we want to use. So S equals R theta, because we know the arc length here is the 8500. We know the radius is 4000, and the only thing we don't know is theta. So you just use algebra to solve for theta. And here theta will be 8500 over 4000, which of course is when all is said and done, 17 over 8. And they want it as a decimal, so I'm going to get my calculator to figure out that. It's easy. 17 divided by 8 is 2.125 radians. Remember, this formula always gives you radians. Always has to be in radians. 2.125. And then, apparently we need it also in degrees. So you just take 2.125 and multiply by the converting factor for today, 180 degrees over pi radians. Radians cancel out, and we end up with times 80 divided by pi. Oh, great. There it is apparently 121 point, round to the nearest whole number, so 122 degrees. Okay. The next one, I already did this. I removed it for you. Okay. So hopefully that clears out at least some of the. Use a circle from the two angles. That's a coterminal one. Okay, I think all the other ones will be okay. Express the angular speed in radians per second. 5 revolutions per second. So if you have 5 revolutions per second, again, you can convert that by noting that there's 2 pi radians and 1 revolution. So it'd be time. So you'd have 5 revolutions per second per 1 second. And then you just times it by this converting factor. In 1 revolution, there are 2 pi radians. And then the revolutions cancel, and you're left with 10 pi radians per second. Okay, so angular speed 10. And then I need the little pi symbol, radians per second. Okay. So hopefully you'll be able to handle those. If you have any questions, you can get a hold of me during my office hours or shoot me an email, and I'll be happy to help you. Okay. So don't send me the email through well, maybe you can. Can you? Yeah, I guess you can ask me here, and it'll send me an email. Yeah. Okay. Okay, so that'll do it, and I think I'll leave it at that, and we'll see you next time.